Okay, thanks a lot. So let's get started. First, I'll introduce myself. So I'm Andrew Alberts. I'm a data scientist at Intact, which is the largest property and casualty insurance company in Canada. So my workshop today is, as it was stated, practical deep learning and computer vision. So I'm going to walk through a practical example of how we can use deep learning to classify images. So one thing that you're probably wondering is, why is this guy from an insurance company giving a presentation about deep learning, something so, sophisticated and technical? Well, the fact is that Intact is trying to become a leader in the insurance industry in the field of machine learning and big data. So deep learning is essentially one of the main tools that we use in our day-to-day work. So it's very important to know about. Now, another reason why I'm talking about this today is that I've been a mentor at a hackathon a couple years ago, and I noticed that a lot of people were using open APIs from Google and AWS to do computer vision applications, which I think is really great. But what I want to do is sort of take a step back and look under the hood and understand how these computer vision systems are actually built, and really give you guys the basics you need to sort of build your own such systems and really learn how easy it is and how easy it is to get started. So without further ado, let's jump into the agenda. So first, I'm going to just give a very high-level overview of what deep learning is. It would be great if you already have some knowledge coming into this about neural networks and deep learning, but if you don't, hopefully the overview will give you some rough idea. Then I'm going to sort of walk through a quick example of how neural networks are applied to images, so that we can sort of tie together the idea of deep learning and computer vision and tie those two together. And then after that, we're going to go right into the demo. So it's going to be a hands-on example with Google Colab. So I'm going to show a model, and we're going to improve it by over 4 times the baseline. We're going to learn the fundamentals of the popular deep learning framework Keras. And if anybody wants to follow along with the code, just go to that GitHub repo and check out the IPython notebook. So, okay, deep learning overview. The role of deep learning, or machine learning more generally, is trying to learn or trying to derive from data a rule which helps accurately predict a label from the data. So basically, you have a big set of data, and you have some labels associated to the samples in the data. You want to say, how can I basically derive some formulas where I can grab a sample of data and get a good prediction of what the label of that sample is. So straightforward example, you may have already heard of this one, is given a set of pictures of cats, which we label 0, and dogs, which we label as 1. Find an algorithm that can be applied to the individual pixels of the image, which will correctly output 0 when we give it an image of a cat, and output 1 if we give it an image of a dog. So I talked about the concept of a rule. What is the rule here? So the rule is just the neural network, which is essentially a series of additions, multiplications, and usually nonlinear activation functions, which help us basically spit out the correct label. Then I also talked about the notion of wanting to do this accurately. So how do we know that something's accurate? Well, what we do is we test that rule, as I said, on a large number of data points we know the true label of. And then we basically calculate a simple ratio. So the number of instances I labeled correctly divided by the total number of samples that I looked at. And this gives you a proportion or a percentage, right? So if 90 out of 100 of your samples were labeled correctly, you would say that the machine learning model has 90% accuracy. You want that number to be as big as possible. 100% accuracy is really the ideal state that you're trying to get at. We won't get to 100% accuracy in the demo today, but we'll build towards that. So neural networks applied to images. So the cats, dogs, example that I talked about is an instance of image classification. So image classification is where you say, well, I take an image and I classify it into one of any number of categories. And this is a fundamental, I would say, application of computer vision. There's more complex areas of computer vision, but this is a simple one, and it's really easy to, I think, get our heads around. So I'm just going to walk through an example. You have an image of a cat. Next, what happens is that you convert it into something called a tensor, which is a numerical representation of the image. As you probably know, images are represented by pixels. Every pixel has a numerical encoding, so usually 0 to 255. So that's the numerical representation. So you convert the image into this tensor. You can think of it as a big vector, if you'd like. And then you pass this tensor into your neural network. So you've got the input layer, which is that vector that I talked about, then a series of hidden layers. So these layers of computations, basically every node performs a series of multiplications, additions, and applications of something called a nonlinear activation function. And then those computations get passed on to the next layer, and you can have as many layers as you want, build it as deep as you want. And then at the end, you structure your neural network such that you have an output layer, and there your aim is to, in this case, predict 0 or 1, 0 if it's a cat, 1 if it's a dog. Okay, so onto the demo. For the demo, I'm going to be using Google Colab and Tensorflow and Keras. So Keras and Tensorflow are very popular frameworks for deep learning and neural nets. And Colab is a tool put out by Google, and it makes it really easy to use basically all the tools that we need, and it gives us easy access to a GPU, which is also required. So again, I have the link to my repo on the bottom of the screen. Now, roughly, what's the aim going to be? So we're going to have a bunch of pictures of cars, and our aim is to build a neural network where we're able to accurately predict what the make of the car is. So I'm going to move out of this deck. So if anybody's following along here with the repo, this is the repo, and just come here, click DL and CV tutorial.ipynb, and it should open up. And if you really want to follow along in Colab, just click Open in Colab, and it'll take you right to this thing. So let me try to make this full screen. Okay, so just an overall agenda for this demo here. I'm going to go through a very quick notebook setup, then talk about loading the data preprocessing. Then I'm going to show 3 different types of neural networks. So one is a fully connected neural network. Then one that's more popular with images is the convolutional neural network. And at the end, I'm going to show an application of a fairly sophisticated neural network architecture called Resnet. And Resnet is really where we see a big improvement. So, okay, for the general notebook setup, you're first going to want to set up a GPU. So GPU stands for Graphical Processing Unit, and it's very important for deep learning. It's really going to speed up your computations. So to do that in Google Colab, you're just going to come, okay, well, I'm having trouble getting there. So come up here to Runtime, go to Change Runtime Type. For hardware accelerator, choose GPU and save it. Okay. So now you're probably going to want to check that you have access to the GPU. So you can run this cell here. We also import TensorFlow at this point. As I said, TensorFlow is really one of the important frameworks for deep learning. So let's see if this runs. Okay, so /device GPU 0. This means that we have a GPU. And I also quickly checked the version of TensorFlow. So we're using TensorFlow 2.4.1. So for the sake of reproducibility, we're going to set some random seeds. Now, when you use GPUs, it's sort of hard to get fully reproducible results just by the nature of how the GPU works, but we'll do this anyway. And so I've actually got my data in a Google Drive. So I'm going to set this to true. But if you're just following along, set this to false. And what's going to happen is that TensorFlow is going to download the data set that we need, right? So just to talk to you about how that works, you can import TensorFlow datasets as TFDS. And then you're going to use tfds.load and tell it that you want Cars196. And it's automatically going to download the dataset for you. So you're not going to have to do any other type of download on the side. This will do it for you. And it'll split the data set up into a training data set, a test data set, and there's also going to be a component called DSInfo. And this is mostly metadata for your data set. Now, if you're trying to follow along, I noticed that the last time I tried this, the data set failed to load. So I don't know, I guess there's a bit of an issue with the HTTP request, but I'm going to assume that it's going to be fixed within a few days. Now I'm going to make a comment here about the difference between a training set and the testing set. So the training set is the data that our model is going to use to train, right? So it's how we're going to actually derive the rule. And then when it comes to assessing the accuracy of the model, we're going to use the test set. So the test set is data that the neural network has never seen before. So regarding the types of this DS train and DS test, they're basically TensorFlow dataset objects. So these are classes that really facilitate the use of different data sets. And we can easily visualize what data we have with tfds.visualization.showExamples. And we just pass it DS train and the metadata. And this gives us a nice visual display of the different samples that we have in the data set. So here we've got a Land Rover, got a Ferrari California convertible. And you'll notice that, so for example, Land Rover is indicated underneath the image. So that's actually what we would call the label of that sample. So all of the data that we have already has an associated label to it. And having the label is very important because we need to know this image label relationship in order to actually build a neural network. If we have no labels, we can't actually train anything. Okay, so as I said, in this initial data set, there's 196 different classes of vehicles. So for example, AM, General Hummer, SUV 2000, Audi, TT Hatchback 2011. So these are all in the form, the make of the car, the particular model, and the year. So that's how they're represented in text, but they're also represented numerically. So this one's represented as 0. This one's represented and indexed by 18. It's important that you have a numerical representation of a label, because anything that you put into a neural network or anything that comes out of a neural network has to be represented numerically, because ultimately training a neural network implies performing a large-scale numerical optimization. So numbers are critical here. So let's see how these different samples are, I'd say these different samples are actually represented. So I have a function called show tensors. I just built it. And so what it's going to do is that it's going to tell us, okay, so for the image, we have a tensor that's 300 by 400 by 3. So this is the dimensionality of the image. So the height is 300, the width is 400. And so what's the 3, right? So the 3 is the number of channels every pixel has. You probably know that images are represented red, green, blue. So the 3 there's one number for the red component, one number for the green component, and another number for the blue component. So that's why the dimensionality of this tensor is 300 by 400 by 3. And so the labeled tensor is just actually a scalar. So there's no dimension shown here. If you want to just visualize one of the images, what you can do is take a sample image and use matplotlib pyplot and use plt.imshow. So basically you take the sample image, which is a tensor, and you convert it to a NumPy array with .NumPy, and then you can just view one of the samples. It's always good to get a feel for your data and look at some individual samples. Okay, so now we're going to move on to data pre-processing. One thing I want to do is remap the classes a little bit. So I said earlier there's 196 classes. What I want to do is map it down to fewer classes. So I had the make of the car, the model of the car, and the year of the car. Let's just concern ourselves with the actual make of the car for this tutorial, just to simplify things. So I've got a function to convert what I call the label string. So that would be the big description of the sample down to just the make. So you can go through this logic on your own time. It's fairly straightforward. It's just a way to extract what the make of the car is. Then this def get new label function maps basically the old numerical representation of the label down to a number that's between 0 and 47, right? Because now we've only got 48 classes. So some examples of the classes that we have are Mercedes-Benz, Tesla, Toyota, Chrysler, Ford, and 40-some other classes. When it comes to dealing with images, something we definitely want to do is normalize the image. So this involves reshaping the image. So you probably remember that the images were like all different heights and widths. You want them to be constant, right? So you always want to have the same height and the same width, because the neural network is going to rely on this consistency, or else if you give the neural network something of a different dimension, it's not going to know what to do. So that's the first thing that this function is going to do. So we're going to give it an image, and it's going to resize it to 150 by 150. Another thing that we want to do is divide every pixel value. So recall I said pixel values are between 0 and 255. So we're going to map that down to numbers between 0 and 1. So that's why we do this division by 255 here. So what does a resized and normalized picture look like? So I'm just going to use that plt.imshow function again and normalize the sample image. And you see it doesn't look as good as it used to, right? Because it got reduced in size. But I think you can still more or less make out the fact that it's a car, and you can make out the sort of important attributes of this car, just visually speaking. So now what you're going to want to do is apply those renormalizations and label remapping to the training set. So you do ds_train.map. .map is just an attribute of this data set, or it's a method of the data set, I should say. And you pass the function, so this relabel and reshape function, to the training set. So now if we check the dimensionality of the images, you see you got 150 by 150 by 3, and another image you've got 150 by 150 by 3. So now we've convinced ourselves that the reshaping has done what we intended it to do. So that's good. One more aspect of data preprocessing is taking out the average, or zero centering everything. So our pixels are now all between 0 and 1. What we actually want to do is compute the mean of the pixel values and subtract that from all of our images. That makes training these neural networks a lot easier, and it seems to improve performance. So what you're going to do is iterate over the training set, grab every image, add it to a tensor called the total tensor, right? Do that for every image. And then the average tensor is just going to be that total tensor divided by n, which is the total number of images you have in the training set. And then we apply map again with this center images function, which just takes an image and subtracts away the average tensor. And we applied that to the training set. And everything you apply to the training set, you want to apply to the test set, or else things just won't work out. So to the testing set, you apply the relabel and reshape function. You also apply the center images function. Okay, cool. So our notebook set up, we've We've pre-processed the data. Now let's actually go on to the cool thing, which is building neural networks. The first neural net that I'm going to build is just a run-of-the-mill fully connected neural network. Now this isn't the ideal type of neural network for images, but I'm including it more for pedagogical purposes so that we can all see, what's just a fully connected neural network. Before I go there, however, I just want us to take a moment to think about what accuracy we will need to beat, right? So, you can build any neural network and assess the accuracy, but you kind of want to know what's the baseline accuracy if I just did something really simplistic. So one way of assessing that is you can ask yourself, all right, what would happen if when I tested the model, I would just predict every instance comes from one class, let's say the dominant class in the test set. So you can do that calculation and run that calculation, and you would see that you would get an 11.12% accuracy. So let's say you were to predict Chevrolet all the time. That would give you on its own an 11.12% accuracy. So that means that the neural network that you build better beat 11.12%, or else you kind of wasted your time. Now, before throwing any data into the neural network, we're going to create batches of data. So all this really means is that we sort of take a bunch of images, so in this case 128 images, and put them into batches. And what happens is that when we train the neural net is going to see 128 images basically in one iteration, and then it's going to compute the loss on that, and then it's going to back propagate the updates on the weights. And you can play around with how many images are in your batch. Okay, so now let's actually fit the neural net here. So we're going to use Keras, and all you really have to do is as follows. So our neural net is also called a model, so we call it model equals to tf.keras.models sequential, because we've got a sequence of computations essentially. The first thing that we're going to do is that we're going to flatten the image. So we're going to take that image, which is 150 by 150 by 3, and turn it into just one really, really long vector. Then we're going to pass it to a dense layer, okay, with something called a ReLU activation function. So that's the nonlinear activation function that I was talking about a little bit earlier. And then at the very end, we're going to pass all of that to a dense layer with 48 outputs. Here, 48 is important because you've got 48 classes, so you need to specify 48 outputs. However, in this case, in this dense layer, 50 is more or less an arbitrary choice, and it's something that you can tune or play around with based on your own intuition, let's say. Then what you do is you compile the model. So you need to set an optimizer. Basically, this is the optimization technique that's going to be applied to actually training your neural network. You're going to have to specify a loss function. So as I said, training a neural network is all about performing an optimization. And when you do an optimization, you have to have a loss function to say, well, we want to minimize this loss function. If you get to the minimum of the loss function, basically your neural network should be performing well. And then we want to track a metric. So we want to track the accuracy. So this is basically in line with the notion of accuracy that I presented during the presentation. So, and this number is, as I said, hopefully going to be bigger than 11.12%. Then you fit the model. So you pass the training data. You pass the number of epochs, which is, in this case, 10. That means that the neural network is going to basically chew over our entire data set 10 times. And then the validation data is going to be ds_test. So we're going to look at the accuracy on this held out data set to really get a proper view of the accuracy. So you do that. When you do that, you're going to get all this output. So every epoch, you're going to see the loss value, the accuracy value. It's easier, however, to visualize this. So in blue, we have the training loss curve, which we see is going down, which is good. That means that the neural network is getting better every epoch. However, the testing loss is going up. This is bad because this means basically that we're learning on the training set, but we're not able to generalize to the test set, sort of overfitting, if you will. And on the accuracy, so again, in blue, the training, we get up to an 80% accuracy. However, in the testing set, we've got an 8% accuracy, which is worse than 11% and is just really bad, though it's not surprising since we're using a very simple model. We can check the model predictions. So our model predicted Mercedes-Benz for this, and it's actually a Ferrari. Our model predicted a Dodge for this, while it's clearly an Audi. You can see the logo right there. And here, our model predicted Chevrolet, and it's actually a Geo. I believe Geo was actually a subsidiary of Chevrolet, so it's not such a big mistake, but we really want to get things right here. So some quick tricks here. We've got the model object, so you can extract the summary just to get a quick summary of the model architecture. You can also visualize the model architecture with plot model from Keras. So I also trained a CNN. The difference between the CNN and the previous model is that this uses basically a convolutional layer. So this is definitely something you'd want to read up upon a little bit on your own time. But instead of basically splitting up the image into some long vector, which sort of breaks apart the structure of the image, we keep the image as is, but we apply filters to the image, and that's how we extract our features. So we put a convolutional layer, then a max pooling layer, which sort of filters down the size of the output of the convolutional layer. Then we flatten it, and then we pass it to a dense layer, again with 48 outputs. Similar type of optimization, so I won't go over that again. We do 20 epochs. And again, if we look at the loss curves, there's definite overfitting. And if we look at the accuracy, so on the training set, we get basically up to 100% accuracy. And on the testing set, we only get, just below 13% accuracy. So we beat the 11% benchmark, but we're still not really doing that great. For the sake of, I built a deeper convolutional neural network, just for the sake of it, to see if maybe I could improve on the score. And here again, on the training set, we get 100% accuracy. On the testing set, however, we're still below 13%. So, it seems like we're kind of in a bad place. Like, we can go through as many architectures as we want, and still not really get a good result. So you might want to give up at this point, but you don't have to give up, because there's one last trick. That last trick that I'm talking about is called fine-tuning. So what we're going to do is that we're going to take an existing model called Resnet 50, which is a very deep neural network, and it's famous for being very good on different data sets, particularly images. So we're going to take this architecture, which has been pre-trained on ImageNet, which is a big repository of images, and we're going to use that as our starting point. And then we're going to train on top of this network, and hopefully see some improvements. So what you do is, from Keras, you import Resnet 50. Again, with the weights being those trained on ImageNet. You set your input tensor shape to what we've been using, so 150 by 150 by 3. And then you can check out a Resnet summary, resnet.summary here. What you really care about is at the very end, so you can see that Resnet is very complicated just by the summary. So what you really care about here is what the dimensionality is of this last output. It's 5 by 5 by 2048. Now what you want to do is set your new model to be the output of the Resnet model. And then you want to add an average pooling 2D layer with pool size 5 by 5. And it's 5 by 5 because this last layer is 5 by 5. Then you flatten that output. You add a dense layer. You apply dropout, which I'm not going to get into what dropout is, but it's a form of regularization for neural networks. And then you do as we did before. So add a dense output layer with 48 outputs, because again, we've got 48 classes. And that's the architecture of your model. Then you compile it and you fit it. So here I trained it over 18 epochs, and let's see what it gave us here. So, okay, for the loss curves, you see that the blue, the training, it goes down as before. Now the loss on the testing, it goes a little bit crazy, but you can kind of see that it starts off, you know, at let's say 3 point something, and it starts and it ends off sort of below 3.5, and that's kind of what you want to see in a loss curve, that it goes down over time, not it going up over time as it did in the previous examples. Now on the accuracy front, on the training, you know, we were getting up to, well, let's say 90% accuracy, and finally here on the testing accuracy, you can see that we got up to close to 50% accuracy. So remember that our accuracy to beat was 11%, and then our convolutional network got 13%, and our fully connected model got like 8%. So finally, using Resnet, we're actually, you know, doing somewhat good. So if we check the model predictions now, so recall we got everything wrong basically in the first model. Now we predict Ferrari when we have a Ferrari. We predict an Audi when we have an Audi. We predict even a Geo when we have a Geo. We predict a BMW when we have a BMW. And we predict Rolls-Royce when we gave it a Mercedes-Benz. So in this last example, we made a mistake on this prediction. But I guess here what the neural network learned is that these are both cars that I cannot afford. So that's roughly it in a nutshell. How to get started on applying deep learning to computer vision problems. I hope you've been able to see that it's actually fairly straightforward, and it's even easier to do if you've got access to Google Colab, which you all do have access to. So Google Colab gives you access to a GPU as well, which is quite necessary to train these computer vision models. So thanks a lot, and I don't know if I have time for questions.
Yeah, if there are any questions, feel free to drop it in the Q&A or chat.
Okay, so one question I see is there any reason why Resnet was chosen over other models? So, I mean, Resnet is fairly popular and it has a good reputation, and it's one of the more recent and easily available models to choose from. There's also things like VGG16, which is older than Resnet, but I mean, Resnet's really well known, and it tends to work. So,
I think there were two questions. Could you go over what is an epoch?
Yes, so as I said, an epoch is basically just one iteration of training that goes over the entire data set. So you've got batches, right, which in this case were of size 128, I believe. So that's a batch. And then once you go through all the batches, that's an epoch.
And the next one is, do you have any resources for beginners wanting to learn deep learning, I think?
Any resources? Yeah, that's a great question. I think YouTube is always a great repository of knowledge. So I would go with YouTube. There's some great series of lectures by Stanford University that I even used as sort of a resource for this talk. So if you just go to YouTube and type in Stanford University deep learning, that's a great resource.
I think those are the questions for now.
Awesome. We'll wrap it up then. Thanks for hosting this workshop, Andrew. This gave us really great insights on deep learning and machine vision. So if anyone has any questions, feel free to message on the sponsor Intact channel.